according to the cloud. All right, we've got a little bit of work to do today. We've got a homework 5, which is due on Monday. That's the 1st of March. And then we have a homework 6, which is due a week after that. We've got a reading assignment. That's chapter 4. And in homework number 5, we have a number of K-map questions with don't cares. So this represents a substantial amount of drill work for us. And what I'd like to do, I'm hoping that you guys have had a chance to look at it, is open the floor to questions about homework number 5. Anything that looks like you might need a little help with.
Can we do 16 and 17?
Sure, let's take a look. 16. Use K-maps to simplify the following function in sum of products form, taking advantage of the don't cares provided. Well, it turns out you always have to take advantage if they help you, and they will help you if they make your loops bigger. So F is equal to sigma M of 1, 2, 3, 5, 8, 13 plus sigma don't care on 0. So how shall I approach this problem? Abe, what do you think?
I'm sorry to interrupt. I was actually going to ask you a question about this because I'm a little behind on this. I was going to ask you, how can we access the pre-recorded lectures so I can kind of review for myself?
Sure. So in, let's see, how can I access the pre-record? Have you been to the website, http://www.docjava.com?
Yeah, I've been there. Also, they're on there?
Yes, they are.
Okay, thank you.
Yeah, you click on courseware, and then you click on Digital Design 1, and then I have all of the lectures being uploaded regularly.
Okay, yeah, that's great. I got to do a little bit of review.
Okay, but let's get back to the question at hand. How do I approach this problem?
Would you draw a K-map, Professor?
Absolutely. Let's do a K-map. So it's a 4-variable K-map. Oops. And you can see why numbering K-maps is so critical, right? Because we're being given the numbers. If we write them in the wrong place, it's going to give us wrong answers. So it says here, I got a 1 on 1, 2, 3, 5, 8, and 13. And I got a don't care on 0. And all the rest are 0. And I wonder if somebody would like to suggest something to loop. What's our biggest loop?
0, 1, 3, and 2.
There you go. And with that loop, what product term do I write?
A prime, B prime.
There you go. And let's see now. I think there must be some way to loop element 8. How shall I loop element 8?
0, 8.
Yeah, 0 and 8 will give me a larger loop than if I just loop 8 by itself. And what would the product term be for 0 and 8?
B prime, C prime, D prime.
There you go. Does everybody kind of see that now? How about these other things that haven't been looped? 5 and 13. What's the best loop for that?
Loop them together.
Yeah, let's just loop them. And what's the product term for that one?
B, C prime, D.
There you go. And that's it. That's how you do it. Now, who got a little bit lost on this one? Now, do you still want me to do question 17?
Yes, please.
Okay, we will do that next. So question 17 says, given the following K-map. So we're starting with a K-map this time. And it says here, that I got some ones which are in red. So I'm going to keep them in red in my K-map. And I got some X's which are in black, so I'll keep them in black in my K-map. Looks like they're here and here. And then it says all the rest are zeros in green. So I'm going to try and be consistent with the homework color scheme because it's so really very colorful. All righty then. I suppose for completeness, I should number my K-map. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. By numbering it, I get to reference the actual K-map number that is the cell that I'm planning on doing some looping with. How shall I loop element number 1? Cool. How shall I loop element number 1? All right. How about this? Alex, how shall I loop element number 1?
You kind of cut off, Professor. What was that?
How do you want to loop element number 1?
You would have to do it by itself.
Yes, thank you. And what would the product term be there?
It would be A prime, B prime, C prime, D.
There you go. Thank you. And how shall we loop element number 7? Anybody?
Same thing.
Same thing. And Alex, what's the product term there?
A prime, B, C, D.
Sounds good. And what about this other thing here, number 11? How shall that get looped?
By itself.
All by itself. And what's the product term there?
A, B prime, C, D.
So that's how you do that. In other words, because we had loops that didn't combine with any other elements, we ended up with all 4 variables in each product term. So this K-map didn't result in any simplification. But one thing that did happen was we were able to discard the don't cares. They didn't help us. Any questions about this? This is question number 17. No questions?
On which homework is this?
This is homework number 5. The one due on Monday. Any other questions about homework number 5?
Can you go over question 21? I think it's similar to a question we did in homework 4. To my understanding, the K-map would equal 0, but I just want to make sure I'm clear on
All
that.
right, well, let's have a look at that. That's a really, really good question. Let's see if I can do this. I will make a K-map. Okie dokie. What do we loop?
Can you loop the whole thing?
Sure can. And what is that equal to?
1,
1. So what is F equal to?
1.
1. Someone said it's 0, but how could it be 0? That's what I think. You know, basically, this is the ultimate in simplification. All you need to implement this function is a wire that connects to logic 1, which for TTL would be 5 volts. Any other questions? Well then, I think you guys have pretty much exhausted the questions here for homework 5. Hearing no more questions, I'm going to move on to homework 6. Is that all right with you guys? Everybody's done with homework 5? Going once?
Yes, sir.
All right. Well then, there you go. Let's see now. Course content. I have to learn how to switch without having to flip back and forth. Going to course content. Homework number 6. Edit. All righty. Let's do a little session on how does it work. What I'd like to do is bring up a little device I have here. This is a sample, and I don't know if you can see that, but this is lighting up, and then there's another button in here. I'm going to do this. There, you can see more things lighting up. These are called surface mount devices. These are little LEDs with a difference. They're different from what you're used to because they don't have any leads that you can see easily. They just solder straight to the printed circuit board. So these are, there you can see it. Yeah, there we go. It's a little out of focus. I wish it would focus. Why doesn't it focus? So you can kind of see the camera kind of picks it up. I got blue, I got green. They're very small indicator lights, just the sort of little lights that you would see on a, on a pulse oximeter or on a On an Arduino surface mount board, right? Most of the Arduinos have little surface mount LEDs. And so what happens is you use a little pick and place machine that shoots out these guys like a machine gun onto a substrate with a little solder flux. And that's called a printed circuit board. And then it goes through the oven called reflow oven, and it heats the solder so that it melts. And because there are these pads that accept the solder and a wetting agent called flux, it sucks the little surface mount device right onto the printed circuit board, so you don't have to solder individual leads. You basically can solder the whole board at once. And these LEDs, light emitting diodes, they're a little bit different from what we're used to. Here, I'm going to stop the video, share the screen, back to the whiteboard, and close the whiteboard. Okay, so that's my little demo with the iPad. So I'm holding the iPad with one hand and I'm playing with the LEDs in the other. So how does it work? These are, interesting devices. Obviously they need power, and they are light emitting diodes, LEDs, and they work with a phenomenon that is described in physics. So let's think about this. If we take a battery and we run it into a standard filament bulb, perhaps in our flashlight, with a little bit of a switch, what happens inside the bulb is you have a piece of wire called a filament. It's in this vacuum, VAC, and you have a what's called a tungsten filament. And what happens with tungsten, and this is sort of interesting, it is a metal that has the highest melting point known to man, which means you can get it really hot inside and it doesn't melt. And what they do is they heat it up with this electricity. It makes a little short inside of the bulb, and that creates a lot of heat. And as the heat increases, it creates what's known as a thermal break. And that thermal break essentially increases the resistance, which actually drops the amount of power that's being consumed by the filament. And in addition to heating up the filament, it gets so hot that it starts to what they call incandesce. This is what happens when things get hot. So incandescence allows us to use something that's hot to generate light. So if you take something like a piece of iron and you fire it in a blacksmith's kiln, what happens is it will glow. It'll glow, and they'll say it's red hot, right? That is what's known as an electromagnetic radiation that has been induced by heat from a hot body as a result of its high temperature. So what happens is you get what's known as a black body radiation. So if you take carbon, just regular old carbon, make a cube out of it. Here's the cube of carbon. Drill a hole in it and bore out the hole. Then take the carbon and heat it up to 5,000 degrees Kelvin. And what you get is a white light, which is like the daylight that you see. It is what's known as a 5,000 degree Kelvin Kelvin, what would we call it? An illumination, a calibrated illumination source. So when you go out to the store and you buy 5,000 degree Kelvin fluorescent bulbs for your kitchen, you get what's called a daylight fluorescent bulb. And some people like to use that because it helps keep them from being depressed during the winter when they don't get enough sunlight. And so they call this seasonal affected disorder, or what's known as SADS. And this is like a real thing. People need to be exposed to the 5,000 degree Kelvin light because they need that daylight. It's particularly onerous for people who have to be on lockdown during COVID because they don't get out much. And this can create its own sort of depression. And so that's sort of a big deal. And when people shop for the fluorescent bulbs, they go for this color temperature. Now, fluorescent bulbs do not heat with incandescence because they do not light with incandescence because they light with fluorescence. And fluorescence is a different phenomenon. That is a phenomenon where you have an electron impinging upon a chemical element known as the phosphor. And what it does is it raises another electron to a high energy level. And when it falls to the lower energy level, it emits a photon, usually of lower frequency than the energy that was input. And so that's known as fluorescence. And that does not require high heat in order to be able to give you the kind of luminescence that you might be looking for. Another way to do light, right? Because LEDs they're not fluorescent bulbs, okay? And they're not incandescent bulbs. Instead, what they are is using electroluminescence. Electroluminescence is the result of recombination of electrons and holes across a barrier. So this is another way in which you can generate light. It's very efficient. And what you do is you get two pieces of silicon. Each one is doped. That is to say, one has got an impurity added to it, which has an excess of electrons, and another one has an impurity added to it, which has a deficiency of electrons. The one with the deficiency is known as p-type, and the one with the excess is known as n-type. And then there's a barrier between these two, which we call a junction. And then we give these things names. We call this the anode. This comes from like Michael Faraday. So this is like from the 1800s. And the cathode. And we give it a symbol because energy typically is only going in one direction, although this is not a perfect unit. Some energy can go in the other direction, and it looks like a valve. And so this is the anode, and this is the cathode. And so what we have here is a schematic depiction of the physical semiconductor. And as energy is passed through the diode, we get light from the diode. And so this is an electric field which works very similar to the phosphors in the sense that it's creating high energy electrons, which then fall to a lower energy level and then emit a photon. So excited electrons cause the release of energy as photons, and the photons are, of course, light. And that happens during the recombination of what are known as the electrons and the holes. And this is the foundation for, well, all modern lighting now has an option to use LED bulbs. Some people hate them, but they are available and usually not terribly expensive anymore. So that's interesting. Normally we just use them as little indicator lights like we saw on the surface mount device. So that's an LED. And now you know how it works. There are other ways to generate light, including chemoluminescence, which you can get from fireflies. They actually illuminate things with what's called cold light. And then there's another form of luminescence known as sonoluminescence, which allows you to create extraordinarily high temperatures inside of fluids as bubbles collapse. And that's a fairly impractical way to illuminate, but it's interesting, and it's a totally different mode of illumination. So now we know about LEDs. Isn't that cool? LEDs. Any questions? LEDs. So
Oops, sorry.
yes,
What does it say? Does it say something about filament. What does it say before that? Sorry.
That says vacuum.
Oh, okay, that's what I thought.
And this
And
says
then-
tungsten.
Okay.
Well, it says tongue, actually. I don't have enough room to write. The iPad is very constraining. You know, it's a little sort of thing. They have to, it's supposed to be my whiteboard, so you'll have to forgive me. I suppose I could go back to the camera, but I think it's been universally hated. So we'll stick with the blackboard for now. So that's that. And I thought it was kind of an interesting thing for us to take a look at. I thought also we should have a little bit of an examination of our multiplexers again, only this time with a difference. What we'll do is we'll write a little truth table. And we'll make A our selector. So this will select for C, and this will select for B. And so then the function f will have an output which is equal to, and if you're selecting for C, you just copy C in, 0, 1, 0, 1. If you're selecting for B, you just copy B in, 0, 0, 1, 1. And then if you want to make a little 3-variable K map, I'm going to number this somewhere. I can see I've got a 1 in rows 1 and 3. Let's change colors for fun. And I've got a 1 in rows 6 and 7. And I'm going to loop, and then I'm going to loop again. And this is going to be equal to A prime C. And this is going to be equal to A B. And that is the function that defines a 2-to-1 multiplexer where A is the selector and B and C are inputs. Any questions about that? So what I'm doing now is I'm following along in chapter 4. Very similar to the book with a difference. The difference is he puts the selector in the least significant bit, which makes no sense to me. I think it makes more sense to group things by the selector than to try and make the selector change every single row, because that's just painful. And so now we've got this 2-to-1 multiplexer. Let's take a look at what we can do with it. So here's the 2-to-1. Here's A, here's F, here's 0, and here's 1. Find the truth table for the given 2-to-1 multiplexer. So that's interesting. How do I do that? All right. So the input here is, let's call it B and C. So how do I know? Well, if we write down A, B, and C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. F, when we're in A, this is going to be C. When A is equal to 1, it's going to be all B. And it says here the B input is equal to 0. So F is going to be 0 in through here. And it looks like the C input is going to be all 1s. So F is going to be all 1 and right in through here. How do I know this, right? Well, let's go back. I know this equation, F equals A prime C or AB or AB. And I also know that B equals 1. And it looks like B is equal to 0. And C is equal to 1. So then F must be equal to A prime or A times 0. So it's just equal to A prime. And sure enough, if you look at F, it equals A prime. And if A turns to a 1, it turns to a 0. So that's proof positive with the actual equation for the 2-to-1 multiplexer. But the more interesting thing is we were able to implement this truth table without a K-map. How cool is that? So now I can create truth tables for, well, for arbitrary K-maps, really. Let's do another one. I like this. This has been fun. Suppose we do another 2-to-1 multiplexer problem. Here's a 2-to-1 mux. His input is A. We have, I forget now, is B on the bottom? I guess B, and then C. And then what we'll do is we'll put in D and D prime. And now here comes F. Oh no, what do we do now? Well, it looks like I need 4 variables, right? Oh dear, 4 variables. Well, let's do it anyway. A, B, C, D, 0, 0, 0, 1, whoops, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. You see what'll happen one day when I get old and lose my mind? I'll be walking the streets homeless, and I'll be going 1, 1, 1, 0, 0, 1, 0, 0, 0. It'll just be one of those really sad things. Oh no, he's gone off the deep end. Poor Professor Lyon. Yeah. And then here comes 1, 1, 1, 1. And then here comes F. And somehow we have to figure out what's going to happen. What is going to happen? Well, it says here, B is selected for input 0. Isn't that right? Let's just make sure. No, it's C. C is selected for input 0. B is selected for input 1. That's all right. Let's go back. So this is supposed to be C, and this is supposed to be B. And we know B is equal to D, so we can write 0, 1, 0, 1, 0, 1, 0, 1. And over here for C, it's equal to D prime, so we can write 1, 0, 1, 0, 1, 0, 1, 0. And so now we have derived the truth table, which is kind of cool. We derived the truth table from our little, how you say, 2-to-1 multiplexer setup. Isn't that cool? So your 2-to-1 multiplexer has just implemented a 4-variable truth table, and you didn't need a K-map for that.
Professor, can you go
Yes.
over again how we got 0, 1, 0, 1, 0, 1, 0, 1?
Yeah, so it says here B is equal to D. So I copied D over to here, because when B is being selected, we are selecting for D. And we know what D is. Moreover, over here, C is supposed to be equal to D prime. So I took D and I inverted it and wrote it over here. So this is equal to D prime. And this is equal to D.
All right, thank you.
Yeah. So that's interesting. Let's see if we can't do some more interesting stuff with these multiplexers, because it's gotten, well, sort of kind of cool, actually. Suppose we're given a 74154. 74154 multiplexer is a 4 to 16. Sorry, it's a 4 to 16 decoder. 4 to 16 decoder. So a 4 to 16 decoder says I have, I don't know if I can do it in this space, 0, 1, 2, 3, 4, 5, 6. We better make this bigger. Shoot. Let's start by numbering. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. No, we don't have 16. 0 through 15 is 16. So this is the output, whoops, the output of the 74154. And the outputs are all inverted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And then what we do is we take the selector inputs, oops, here, and the outputs are all going to be product terms that have been inverted. And we take those inverted product terms and we run them into a NAND gate. And this is going to be a 7430. That's known as a octal NAND gate, or an 8-input NAND gate. You can find these things in the stockroom under these numbers. So you can actually find, you may find a variant, 74LS154. That stands for low power Schottky. Or you can find 74HC154. That stands for high speed CMOS. Or you can find it without any of these little extra letters at all, in which case they're just standard TTL. So then we wire up 13, 11, 9, 13, 11, 9, and let's see now, 7, 5, 3, and 1. 7, 5, 3, and 1. So we're wiring up, I'm just going to list them out here. 1, 3, 5, 7, 9, 11, 13, and 15. Those are the terms that are being wired. Find F, given the following schematic. Use canonical sum of products form in shorthand notation. What on earth should we do? Any ideas? Andrew, I haven't called on you. What do you think, Andrew?
So the question was the canonical sum products.
Yeah,
One.
I want to find the canonical sum of products in shorthand notation.
So you would just do
CSOP,
the,
SHM.
so you would just do the sigma with the lowercase m and then 1, 3, 5, 7, 9, 11, 13, 15.
That's exactly right. Does anybody understand that? Who got confused by that answer? Nobody? Really? I don't believe you. Somebody got confused. Well, just to put, not to put too fine a point on it, if you had A prime, B prime going into an AND gate, it's the moral equivalent of an OR gate because of De Morgan's theorem with inverted inputs. And so the inversions cancel and what you would get is A or B. And so what we've done here is we've summed the product terms that are coming out of the decoder. And it has given us an ability to implement a 4-variable truth table with nothing more than 2 chips, a decoder and an AND gate, and that's it. And so no K-maps were harmed by this expression, right? We didn't do an optimization at all. Probably wasted a whole bunch of transistors, but from an implementation point of view, the only thing we needed was 2 chips and some wire. And that lets us wire up our little truth table. So that's convenient, right? Because I don't need to worry about the discretes that I would need otherwise. In fact, if I got a minimum sum of products form, I might actually need more chips than if I just sat down and said, oh, let's use the 74154 in the NAND gate. But those might not be very inexpensive chips. Right, so that's a decoder problem. I think that was a good one. Let's try another one. That was by the way, that was question number 9 in homework 6. Let's try another. These are fun, right? Isn't this fun? Very fun. Very fun. So let's do an 8-to-1 multiplexer. I like that. So there's 7 inputs. And what we'll do is we'll take the first 3 and we'll wire them up to ground. And then we'll take D3, that's right in through here, and we'll wire it to +5 volts. We'll assume that's a 1. And then we'll run D5 and 7 to the same place. And then we'll take D6 and D4 and we'll run them together. So looks like this has got to need a connection. That'll need a connection. And that just makes it more clear, I think. So now this is an 8-to-1 multiplexer. His output is F. How do we find the truth table? Or better yet, find F in canonical sum of products form. So that F is equal to M. What are the indices? Alexa, what do you think about that one? I don't think I called on you before, Alexa. Are you there?
Yeah, I'm not too sure. I'm a little confused.
Okay, fair enough, fair enough. So what happens here is when the input is 0, 0, 0, the multiplexer acts like a rotary switch where the selector points at position 0. And that gets routed to F. And position 0 is a 0. As we go to 0, 0, 1, the multiplexer goes to the next position, and that's also a 0. Goes to the next one with 2, also a 0. In fact, the first time you see anything with non-zero is when it goes to position 3. And once it's at position 3, what we do is we say, at position 3, its output will be a 1. At position 4, its output is a 0. At position 5, its output is a 1. At position 6, its output is a 0. At position 7, its output is a 1. And so what we have done yet again is implemented a truth table without any K-maps, and all we needed was wires and an 8-to-1 multiplexer. How's that grab you? So the MUX is kind of a convenient way to go in terms of implementation, because the only thing I needed was wire, and I got a truth table, which is cool. And as it happens, you can find these in the stock room, and there are a number of variants on it, but I believe it's 74151. Let me just look it up real quick. And that is an 8-to-1 multiplexer, so I am correct. Yeah, it's not much, but it's all I've got. I can remember some of these things. 74151. So the decoder was 74154. That was a 4 to 16 decoder. This is an 8-to-1 multiplexer. So pretty cool, right? Let's do it again, because this was so much fun. Wasn't this fun? The answer is yes, Professor Lyon. Very fun. Yeah, do it again. Do it again. Okay, we're going to do it again. So this time what we'll do is we'll get a little multiplexer in here, A and B, and we'll say that 2 to the 2 is 4. So this is a 4-to-1 multiplexer. 4 to 1. 0, 1, 2, 3. With function f coming out. And the input is going to be C, C prime, 0, and 1. And this is a MUX. Okay, given the following schematic, find F. What will F be? I recommend a truth table. A, B, C, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And I recommend grouping the truth table in 2s. Why on earth would you do that? Well, because the selector is going to act like a rotary switch that selects 0 or 1 or 2 or 3. So here we have selector input 0. Here we have selector input 1. Here we have selector input 2. And here we have selector input 3. So when it's pointing to 0, we expect C to come out. And so we write C. When it's pointing at 1, we expect C prime to come out, and so we invert C. When it's pointing at 2, we expect 0 to come out, so we write 0. And when it's pointing at 3, we expect 1 to come out, so we write 1. And once again now, we have implemented a function without a K-map. And what's interesting here is that we were able to use a simple multiplexer, a 2-to-1 multiplexer with only 2 selector inputs, A and B, but we were able to implement a 3-variable function. Given the schematic, we were able to find the truth table. But it goes the other way too. We could start with the truth table and derive the schematic for the multiplexer. Let's try it that way. So what I'll do, are there any questions about what I've done here so far? Does it make sense to people? Let's do another one because it's so much fun. Wasn't this fun? Very fun. Very fun. I'm going to do a 3-variable truth table. In fact, what I'll do is I'll start with the variables. A, B, C. And what we'll do is we'll write the function. And then we're going to make up a function. 0, 1, 2, whoops. 1, 1, 0, 1. There. I don't know what I'm doing, but I'm not going to let that stop me. And what we'll do is we'll say, given the following truth table, find the schematic for the 2-to-1 multiplexer A and B that implements the truth table F. What should we do? Let's see. Bridget, what shall we do?
I'm not exactly sure.
Fair enough. Okay, let's do this. I'm going to say that A and B act as little channel selectors. Here's A and B right in through here. And when A and B are 0, you're in this area. When A and B are 1, or 0, 1, you're in this area. And when A and B are 1, 0, you're in this area. And when you're down in the bottom, you're in area 3. So that means that if what you want is 0, 1 to come out, then just input C, because that's equal to 0, 1. If what you want is 1, 0 to come out, input C prime. If what you want is 1 to come out, just input a 1. And if what you want is 0, 1 to come out, then input a C. And this is all you need to implement that. What do you think of that one? In other words, you do not need a K-map to implement a truth table if you have the right multiplexer and the know-how to use it. What do you think of that? Is that good? Good explanation? Who got confused? So if you get a 74157, you will have 4 2-to-1 multiplexers in a single package, which you can do whatever you like with. They call that 4 or quad. That's a quad 2-to-1 mux. So in other words, there's 4 of these things in one dual inline package. That's 16 pins. Who got confused by this? Want to do another? I think we should. Let's do one more. Suppose I start with a truth table, ABC, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Let's make up a function. 0, 1, 1, 0, 1, 1, 0, 0. Now let's get our little 2-to-1 mux, A and B and F, 0, 1, 2, 3. All right, how shall we wire up the 2-to-1 multiplexer to implement the 3-variable truth table? Let's call on somebody. Cassie. What should I do, Cassie? Help me.
So could we do the grouping like we did last time by 2?
You bet. We'll group by 2. That's a good way to start. Oops, I'm going to change colors. Here, 0, 1, 2, and 3. Alrighty then. So what shall we write for the inputs now for the multiplexer?
So for 0 would be C.
Yep,
1 would be C prime.
yep,
2 would just be 1 and 3 would just be 0.
yep. That's it. You did it. That's the whole thing. So that's a 2-to-1 multiplexer implementing a 3-variable truth table. But suppose some dastardly person said, oh, let's implement a 4-variable truth table. Oops, make it neat. Here, make it neat. I don't have enough room. Darn it. And now I'm going to give you a bigger multiplexer. I want to go and make an 8-to-1. 0, 1, 2, 3. With inputs A, B, and C to an output called F. So let's see who hasn't gone. Darius. What shall we do, Darius? Any ideas? How about David? Are you with us, David?
Yeah.
What do you think, David? What shall we do?
I'm not really sure.
Well, let's examine this a little bit. If we were to group by 2 rows at a time, then we'd be using selector inputs A, B, and C. So I can do that. And then I can number them 0, 1, 2, 3, 4, 5, 6, and 7. And now what we'll do is we'll say when A, B, and C are equal to 0, we're going to be selecting this input right in through here, the 0 input. And we want F to be 0, 1. So what shall we use for the input?
D.
D, there you go. And what about for input pointing to 1?
D prime.
D prime. You're doing it. What about here?
D.
That's D again. And what about over here? That's a 1. And what about over here?
1.
1 again, you bet. And what about this one?
0.
0. And what about this one?
D prime.
D prime. And what about this one?
D.
That's D. And that's it. So now what's cool about this 8-to-1 mux is it's just implemented a 4-variable truth table with no K-maps. Single chip, the 74157, right? This is called the, sometimes they write 157 because it's understood that the little apostrophe means 74157. And in fact, it refers to the entire family. So you could get an S for a Schottky or an LS for a low power Schottky, or you can get ALS for advanced low power Schottky, or you can get HC for high speed CMOS. They go on and on, but they all have the same pinouts. They all have the same geometry. They all fit into the same breadboard. They just take different amounts of power and run at different speeds. So that's the, I don't know, bird's eye lowdown on the multiplexer caper. Bird's eye lowdown on the multiplexer caper. So that's a, that's pretty cool, right? We've got 2-to-1 multiplexers, 4-to-1 multiplexers, 8-to-1 multiplexers. If an 8-to-1 multiplexer can implement a 4-variable truth table, how many variables do you think a 16-to-1 multiplexer could implement?
Eight.
No. So an 8-to-1 multiplexer implements a 4-variable. So a 16-to-1.
My bad. I meant, would it be 5?
mux will implement, yes, a 5-variable K-map. Truth table. And so if I wanted to use a 2-to-1 mux, I could implement a, well, I'd have a 3-variable truth table because it needs 2 selectors to select for, that would be a 4-to-1 mux. It needs 2 selectors for 4 inputs. So you can always implement a truth table that's 1 more than the number of selectors. 1 more than the number of selectors. So if I have a 2-to-1, I can do a 2-variable truth table. If I have a 4-to-1, I can do a 3-variable truth table. If I have a 8-to-1, I can do a 4-variable truth table. If I have a 16-to-1, then I can do a 5-variable truth table. Yeah. Does it make sense? You can kind of see the symmetry there. So now that's as far up as I go. The 74150, that would be your 16-to-1. The 74151, that would be your 8-to-1. The 74157, that would be your 2-to-1. And the the 74153, that would be your 4 to 1. So what can we conclude about these model numbers? They don't have much to do with what they contain, right? That you would hope that it would end with an 8, and therefore it could be 8 to 1, and I could memorize it more easily, but in fact I can't. I got to look these things up. And so what we use is the TTL data book. And that gives us a clue as to what these things look like. TTL data book. And in fact, you can find all this stuff on the web now. Just Google it. Type in the number and hit enter into Google, and it will come right up. So you don't really need the physical book. But in the days before Google, we were just using the TTL data book. And it's great reading. I mean, you could just sit there and read it all day, take it with you on vacation, read it on the beach. It's just great fun. And once you know the family, you can design the hardware without consulting the book. You can just sketch it out on the back of a napkin and come up with a design. And that makes it even more fun. And these are just the multiplexers, not the decoders. So these are just, this is a TTL, transistor logic family of multiplexers, simple multiplexers, known as medium scale integration, or MSI TTL. They don't need a lot of transistors to make these things. And they're very old. This stuff comes back from like the 70s, early 70s. It's been around a while. And it's in your book. And it's in your book. So you'll see it when you start to read through the book. You'll see some of these numbers coming up, and then you'll know where they're coming from. And you'll know that you'll be able to Google them, and you'll be able to see exactly how the designers are using these things. And it's possible to build full-blown computers, central processing units, with just TTL. In fact, that's what they used to do. And some of the computers which I used had nothing in them but TTL, no microprocessor chips, just TTL chips, and that's it. Pretty cool, right? So that's that's your little introduction to multiplexers and decoders. Let's try some more questions from the homework. I think that would be fun. Let's see. Let's do some multi-level logic. A goes into an inverter, which then goes into an AND gate, which then goes into an OR gate, which then makes a function F. B goes into an OR gate. A goes into the same OR gate. And then we have an inverter. That goes into the AND gate. And we have another inverter. And that goes into yet another AND gate, which goes into this OR gate. And then B goes into an inverter, which then goes into the AND gate. Find F. So this is what's called multi-level logic. Let's see, who do we got here we haven't talked to yet? Eric. What do you think, Eric? How do I do this problem? Given the following circuit, find the Boolean algebraic expression that describes the circuit. Are you with me, Eric?
I'm not really sure.
Let's just break it down. What happens, Eric, after A passes through the inverter? What do we get?
A prime.
Yeah, so that's A prime. That's good. And then what happens after A and B pass through this little OR gate? Right here, what do we get? Any ideas?
A or B.
A or B, that's it. And now what happens over here after A or B go through the inverter?
A prime plus B prime.
Well, it's A or B inverted. And if you wanted to look at A or B inverted and use De Morgan's theorem, what would that give you? Anybody want to help?
A prime, B prime.
A prime, B prime, exactly right. So with A prime, B prime, and the AND gate here, I have A times A prime, B prime. What's A times A prime? That's 1 times 0. So the output here is 0. That's what that is. And what about over here? Here we have A prime, B prime. And over here we have B prime. And they're ANDed together. So that gives me A prime, B prime. And so now I have an OR with 0. And so F must be equal to A prime, B prime.
What number was that?
I would have said it's number 11, but it's not quite the right answer that I see in the answer key. So I'm guessing I must have copied it wrong, because I'm pretty sure the answer key is right. I think what happens here is there should be an inversion on the output here. So I should make sure that I write that in the, that didn't come out nicely in the graph. Let me make sure that we got that. The first NOR gate. The first OR gate is a NOR gate. First OR gate on the left is a NOR gate. It's not showing clearly. So if we update it so that I write it there so that when people encounter it, they will know, it'll change the output substantially, right? Because if it's an OR gate, then we've inverted the inversion. So this is not quite question 11. This is we'll call this a made up question, because if you put this in as an OR gate, you got a totally different answer. And I would work that problem for you now, but we don't have any time because it's end of class period. So what we'll do is we'll put a little dog-eared bookmark on question 11. You guys can remind me for next time. This is, we'll revisit question 11, only this time we'll do it right. And that'll be for our homework number 6. So you've got your reading to do, chapter 11, and you've got a homework due, which is homework number 5. And that concludes the class for today. It's a beautiful day. Enjoy the sun. Thank you.
Thank you,
Thank you.
Professor.
Thank you, Professor.
Thank you.
Thank you,
you.
Professor.
Thank you.